In wide-field survey data, the claim that a small body is accelerating begins much earlier than any discussion of causes. It begins with the simple requirement that the body is real, repeatedly seen, and consistently measured against a stable star field. A moving object is first detected as a point that changes position relative to the fixed background between exposures. The exposures may be separated by minutes, and then by hours, and then by nights. Each time the stars define a reference lattice, and the candidate must step across that lattice in a way that is coherent in time. This coherence is what separates a real object from detector artifacts and transient events. A cosmic ray strike can mimic a point once. A satellite can mimic motion, but leaves a streak or moves too fast and too straight. A known asteroid can be matched to a predicted position. The candidate that remains is the one that repeats and can be linked. That link is made through timestamps as much as through positions. A measured right ascension and declination are meaningful only when paired with the observation time, because the orbit solution is a reconstruction of motion through time. The survey pipeline therefore records a position estimate and a time estimate for each detection. The position estimate comes from centroiding, which tries to locate the center of the light distribution of the object in pixel space, then transforms that pixel location into sky coordinates by fitting to catalog stars in the same image. The time estimate is tied to the observatory clock and must represent the effective midpoint of the exposure. These details become crucial later because an apparent acceleration can be created by a systematic timing bias or a systematic centroid bias. In the earliest stage, however, the purpose is more basic to establish a chain of detections that can be explained by a continuous path rather than by coincidence. Once the chain exists, the object is described as a tracklet on a given night, a short series of positions that define an apparent motion vector across the sky. The motion vector has a direction and a rate. The object may move quickly or slowly, and the rate influences how confidently the centroid can be measured. If the object trails during an exposure, the centroid depends on how the trail is modeled and on the background subtraction. If the object is tracked at the sidereal rate, stars are sharp and the object may trail. If the telescope tracks at the object's rate, the object is sharp and stars trail, complicating the astrometric solution. Survey observations usually prioritize star sharpness for calibration and coverage, while follow-up observations may prioritize object sharpness. The mixed nature of these data is part of the reason early claims of acceleration must be treated cautiously. A small systematic difference between survey centroiding and follow-up centroiding can masquerade as a change in motion when the data sets are combined. The confirmation step is what tightens the identity. A second observatory, or the same observatory on a subsequent night, must recover the object near the predicted location based on the preliminary orbit. Recovery is both a practical and an epistemic test. Practically, it keeps the object from being lost. Epistemically, it shows that the object's motion is consistent with a single dynamical model rather than with a chance alignment. When the object is recovered, the observation arc extends. The arc is the span of time covered by the measurements. A longer arc contains more curvature information, which helps constrain distance and true velocity. In the first nights, the arc is short, and many orbits can fit, including orbits that differ substantially in their future predictions. With each added night, the family of acceptable orbits narrows, and predictions become more stable. Brightness measurements travel alongside positions even at this stage, because brightness affects both detectability and measurement quality. A faint object near the survey limit produces a noisy centroid. Noise can pull a centroid slightly, especially when the background is structured or crowded. If the object sits near a faint background star or galaxy, the combined light distribution can bias the centroid. Such blending is common and often invisible unless images are inspected closely. If the object has a coma, a surrounding haze of dust and gas, the center of light may not coincide with the nucleus. Even a very subtle asymmetry can shift the centroid by a small amount that becomes significant when precise orbit fitting is attempted. Therefore, the initial establishment of the object's track is accompanied by a quiet awareness that the measured position is not an infallible proxy for the center of mass. It is a proxy that becomes more trustworthy when the object is point-like, well above the noise and free of blending. The phrase "accelerating right now" suggests a continuous dynamical change. But in the earliest stage, the only motion that can be stated is apparent motion on the sky, which is a changed direction of a line of sight. Apparent motion is influenced by Earth's own movement and by parallax and by the object's distance. A nearby object can show rapid apparent motion. A distant object can show slow apparent motion. Yet geometry can reverse these simple instincts. A distant object can show substantial apparent motion if the line of sight changes rapidly due to Earth's motion relative to it, and a nearby object can show slow motion if its velocity vector projects weakly onto the sky. This is why early impressions are unreliable. Acceleration in a physical sense is not measured directly from a few angles and times. It is inferred by fitting a dynamical model and examining residuals. In this outermost region, the correct approach is to keep the object as a measured entity rather than as a claim. The measurements are gathered and consolidated. They are checked for internal consistency. Observers verify that the reported times are correct, that the astrometric calibration uses a reliable catalog, and that obvious outliers are flagged. They also compare the object's image shape to nearby stars to assess whether it is point-like or extended. If it is extended, additional caution is applied to centroiding and to the interpretation of early residuals. If it is point-like, confidence increases that astrometry traces the nucleus. The object's identity also becomes more secure as independent detections accumulate. Different instruments have different point spread functions and different systematic signatures. If the same object is measured across diverse systems and the positions line up into a coherent orbit, the case that the object is real and that its gross motion is understood becomes strong. This matters because any later claim of unexplained acceleration must rest on a foundation of reliable identification. If the identification is unstable, what appears as acceleration could be a misassociation of detections from multiple objects. Such misassociations are rare when follow-up is strong, but they are a known failure mode in the earliest stages of linking sparse detections. Therefore, the integrity of the track is the first requirement. By the end of this stage, 3I Atlas is not yet an object that is known to accelerate. It is an object that is known to move to be recoverable and to carry a growing arc of astrometric and photometric data. The groundwork is set for the next steps, translating angles into a three-dimensional orbit, tightening uncertainties until predictions can be tested, and only then asking whether a residual pattern remains that could legitimately be described as a non-gravitational acceleration. Until that point, the only responsible statement is that the object is tracked through repeated time-stamped detections, and that the quality and consistency of those detections will determine whether any later claim about acceleration has measurable content or is merely the echo of early uncertainty and mixed observational conditions. Once the object is confirmed as a coherent moving target, the measurements are still only angles on the sky. Each right ascension and declination is a direction from a specific observatory at a specific time. The work of orbit determination begins by translating these directions into a three-dimensional trajectory consistent with dynamics. This translation must respect the fact that the observer is not stationary. Earth rotates, shifting the observatory's position by thousands of kilometers over a night, and Earth orbits the Sun, shifting the line of sight, baseline, by many millions of kilometers over months. An object's apparent drift across the star field is therefore a combination of its own motion and the observer's changing vantage. A headline about acceleration often ignores this complexity, but the data do not. The data carry the imprint of geometry first, and only later allow inferences about forces. Each observation can be expressed as a line of sight vector. A direction on the sky defines a ray in space. The object lies somewhere along that ray, but the distance is unknown. With multiple observations at different times, many rays exist from different observer positions. The object's trajectory must pass through the set of rays at times consistent with its motion. In a purely geometric sense, a single straight-line motion in inertial space would not fit, because gravity curves trajectories, and because Earth's movement changes the rays. The orbit solution is therefore found by choosing an initial state, a position, and velocity at a reference time, and integrating the motion under a force model to predict where the object will be at each observation time. Those predicted positions are then projected into predicted sky directions, as seen from each observatory at each time. The differences between predicted and observed directions are residuals. The orbit parameters are adjusted to minimize those residuals. In the early stages, distance is the weakest link. A short arc can be fit by a wide range of distances and velocities. A closer solution requires a higher true speed to produce the same angular rate. A farther solution requires a lower true speed. These trade-offs can produce orbit solutions that differ dramatically in implied orbital size and energy while still matching the sky positions within measurement errors. This is why early classification of an orbit as bound or unbound can be unstable. It is also why early talk of acceleration can arise spuriously. If the orbit solution changes as new data arrive, the predicted track changes, and earlier predictions may appear wrong. But wrong predictions early on often reflect uncertainty, not a force. Only when the orbit is tight enough that predictions would be stable under gravity does a persistent residual pattern indicate a real additional acceleration. Parallax provides leverage on distance. Parallax is the apparent shift of the object's position when viewed from different locations. Within a night, Earth's rotation changes the observatory's position enough to produce a measurable parallax for nearby objects. Between observatories, differences in geographic location can provide a baseline even on the same night. Over weeks, Earth's orbital motion provides a much larger baseline, making parallax a powerful distance constraint. As the arc grows and the baseline widens, distance becomes less degenerate. The orbit solution narrows, and the range of acceptable trajectories shrinks. This is the transition from a candidate path to a predictive ephemeris that can be tested. Time is equally important. The observation time must be precise and must be expressed in a consistent timescale when compared to ephemerides and to rotation of Earth. A systematic time offset shifts the predicted direction for a moving object, typically along the direction of motion. If the object is moving rapidly on the sky, a small timing error can create an angular offset that looks like a positional residual. If timing errors vary between observatories, they can create observatory-dependent residual patterns. If timing errors are stable within one instrument, they can create a persistent offset that might be misinterpreted as an acceleration if the orbit model is forced to fit through it. Therefore, careful orbit work treats time as a measured quantity with its own potential biases, not as a perfect input. The conversion between coordinate frames also matters. Observations are made from Earth-fixed locations, but orbit integration is done in inertial frames. The transformation includes Earth rotation, Earth orientation variations, and the precise position of the observatory. Even a small error in observatory coordinates can shift a predicted line of sight. For most purposes, this is negligible, but for high-precision residual analysis, it becomes relevant. Similarly, the transformation from predicted object position to observed direction must include light travel time and aberration. Light travel time means the observed direction corresponds to where the object was when the light left it, not where it is at the time the light is received. Aberration means the observer's motion shifts the apparent direction of incoming light slightly. These corrections are standard, but their importance is that they remove known sources of apparent drift so that residuals are not inflated. The phrase "accelerating right now" often conflates apparent acceleration on the sky with physical acceleration in space. Apparent acceleration can arise even under pure gravity because the projection of motion onto the sky changes with geometry. A body moving on a smooth orbit can appear to speed up or slow down on the sky as its distance changes and as viewing angles change. For example, as an object approaches Earth, its angular speed increases. As it recedes, angular speed decreases. These are not additional forces. They are consequences of geometry. Therefore, before any physical acceleration beyond gravity is inferred, the geometric and gravitational projection must be modeled. Only the residual after that modeling carries meaning. A further complication is that the measured sky position may not represent the nucleus. If the object has a coma, the light distribution can be extended and asymmetric. The measured centroid can shift with seeing with aperture and with the evolving coma. This can introduce apparent changes in position that are not due to motion of the nucleus. In a short arc, these shifts can be absorbed into the orbit solution as changes in distance and velocity because the fit is flexible. Later, as the orbit tightens, these shifts can appear as residual patterns. Therefore, the geometry stage is also the stage where analysts begin to ask whether the object is point-like or extended, and whether different measurement methods produce consistent positions. As the orbit becomes better constrained, the object's motion can be described in a more stable way. The path can be integrated forward to produce a predicted ephemeris with small uncertainty. Observers use the ephemeris to point telescopes and recover the object. Each recovery confirms the geometry and tightens the orbit further. In this stable regime, the question of acceleration becomes meaningful. If under a gravity-only model, the predicted positions are consistently offset in a way that grows with time, the residual pattern suggests a missing acceleration term or a persistent measurement bias. If the residuals remain randomly scattered around zero at the expected level, the object is not accelerating beyond what gravity predicts to the level of detectability. Thus, in this region, the work is to prevent premature conclusions. The object's motion is reconstructed from angles and times, with the observer's motion included, and with corrections for light and frame effects included. The result is a gravitationally consistent trajectory that is refined as the arc grows. Only after this refinement can the phrase accelerating right now be grounded in a specific residual pattern that cannot be removed by ordinary geometry and gravity. Until then, what is observed is apparent drift, and apparent drift is a blend of many motions. The translation from that blend to a claim about forces is the central discipline of orbit determination, and it requires enough time, enough geometry, and enough cross-checked data that the remaining residuals can be trusted as a property of the object, rather than as a property of the measurement and the vantage point. As the arc lengthens, orbit fitting moves from a wide family of plausible trajectories to a narrower set that can be tested by prediction. In the earliest phase, an orbit solution is often best understood as a hypothesis that allows recovery, not as a definitive description of the object's path. Short arcs do not constrain distance well, and the orbit parameters that depend strongly on distance, such as semi-major axis and eccentricity, can vary widely while still fitting the measured sky angles. This is the mathematical source of many dramatic interpretations. If an early solution implies a certain path, and a later solution implies a different one, it can feel as if the object has changed course. In reality, the object has not changed. The model has changed because the data have reduced the allowed region of parameter space. This reduction happens because new observations add curvature information and parallax leverage. Curvature in the observed track arises from the object's changing direction in inertial space under gravity and from Earth's changing vantage. When the arc spans multiple nights and weeks, the object's path on the sky begins to deviate from a simple linear motion approximation. This deviation is exactly what allows the orbit to be pinned down. If the object is distant and moving slowly on the sky, the curvature accumulates more slowly, and the orbit remains uncertain longer. If the object is closer or moving in a geometry that produces strong parallax, the orbit tightens faster. Either way, the key point is that orbit fitting is inherently a process of narrowing, and a changing orbit solution early on is a sign of learning, not of acceleration. The fitting process itself is sensitive to data quality. Each astrometric point carries an uncertainty. If the uncertainties are underestimated, the fit will try to pass too close to every point and can produce a solution that is overly influenced by a few biased measurements. If uncertainties are overestimated, real signals can be washed out. In practice, orbit solutions are improved by inspecting residuals and adjusting weights. If one observatory's points consistently sit offset, those points may be downweighted. If some points are clear, outliers, perhaps due to blending with a background star, they may be removed. These adjustments can shift the orbit slightly. From the outside, such shifts can look like the object is behaving strangely. From the inside, they are the expected consequences of building a consistent data set. There is also the issue of mixing data types. Survey astrometry often has different systematic properties than targeted follow-up astrometry. Survey images prioritize coverage and may not be optimized for faint object centroiding. Follow-up observations are often optimized and can produce higher precision. If survey points are weighted too strongly relative to follow-up points, they can pull the orbit in a biased direction. Later, when follow-up dominates, the orbit can shift back. This can create a perceived transition. A careful analyst therefore ensures that the weighting reflects realistic precision and that known survey systematics are considered. This is especially important when the object is faint and near the survey limit, where centroiding biases can be larger. The early orbit's uncertainty is not just a single number. It is a shape in parameter space. Some combinations of parameters remain correlated. For example, distance and velocity can trade off. If the object is placed slightly farther away, the required velocity changes to match the observed angular motion. This correlation means that certain derived quantities like orbital energy can remain uncertain even when the sky path over the next few nights is predicted reasonably well. This is why an object can be recoverable while still having an uncertain classification as bound or unbound. In this regime, claims about acceleration are often based on the instability of derived parameters rather than on a true residual drift. The correct practice is to focus on predictive performance. Does the orbit with its uncertainty correctly predict where the object will be seen next? And does that uncertainty shrink as expected when new data are added? A true non-gravitational acceleration, in contrast, produces a different signature. When the orbit is already tight, and when the gravitational model is complete, predicted positions should remain accurate. If the object experiences an additional acceleration, the gravitational model will begin to miss. The miss will not look like a random scatter. It will look like a systematic drift that accumulates. Early in the arc, this drift can be absorbed by adjusting the initial state because the orbit is flexible. Later, as the arc grows, the same drift becomes harder to absorb without leaving structured residuals. This is why non-gravitational effects are often discovered after an object has been tracked for some time. The arc must be long enough that the additional acceleration cannot be hidden inside the initial condition adjustments. The phrase accelerating right now also implies a timescale. A small acceleration may be present continuously, but its detectability depends on the length of time over which it acts and on the precision of measurements. Over a few days, many small accelerations produce tiny displacements that are comparable to measurement noise. Over weeks and months, those displacements grow and become measurable. Therefore, a responsible claim of acceleration requires an arc long enough to separate the effect from noise and from systematic biases. It also requires that the data span a range of observing geometries and that the orbit is constrained enough that the acceleration cannot be traded off against distance and velocity. Without these conditions, the phrase is not supported by the mathematics of orbit determination. The evolution of the orbit solution can therefore be summarized as a progression from recovery-oriented uncertainty to prediction-tested stability. In the recovery-oriented phase, orbit elements can shift and uncertainty regions can be large. In the prediction-tested phase, elements stabilize and residuals become the main diagnostic. If the orbit continues to shift significantly with each new batch of observations, it usually indicates that the arc is still insufficient, that the object is difficult to measure, or that systematics are present. It does not usually indicate that the object is changing its motion in an anomalous way. The object's motion is smooth under gravity and smooth under most non-gravitational forces as well. Sudden changes are more commonly due to data issues or to physical outbursts that also change brightness and morphology. Therefore, if a headline claims an object is accelerating right now, the first internal question is whether the orbit is in the stable regime. If it is not, the claim is premature. Another aspect that complicates early interpretation is that acceleration in orbit fitting is often parameterized, not directly observed. Analysts may fit a non-gravitational term and find a non-zero value. But if the arc is short, the fitted term can be poorly constrained and correlated with other parameters. A non-zero fit does not necessarily imply a real force. It can be a mathematical artifact of trying to account for small biases. The fit becomes meaningful only when the term remains non-zero across independent data sets, and when it improves predictions beyond the fit interval. By the end of this region, the concept of acceleration is held in reserve. The object's observed motion is now captured by an orbit solution that is becoming stable. Uncertainties are quantified, and correlations are understood. The orbit is good enough that observers can recover the object without searching large areas. The stage is set for a meaningful definition of acceleration that goes beyond the natural curvature of orbital motion. The next inward step is to define precisely what accelerating right now must mean in the language of residuals, a coherent, statistically significant mismatch between the best gravitational prediction and the measured sky positions persisting after uncertainty is accounted for. Without that definition, acceleration remains a word. With it, acceleration becomes a measurable pattern that can be tested against measurement chain vulnerabilities and against known non-gravitational mechanisms. Once the orbit enters a regime where predictions are stable and uncertainty is small, the data allow a careful definition of what accelerating right now means. In this context, acceleration is not the ordinary curvature of an orbit under gravity, because that curvature is already in the model. It is an additional term implied by a persistent, structured residual pattern. Observed positions diverge from gravity-only predictions in a way that is larger than realistic measurement error, and that grows or evolves coherently with time. The residuals are not just numbers. They have direction, they may have dependence on solar distance, and they may show changes that align with changes in brightness or morphology. A headline may declare there is no natural cause, but the measured content of the claim is always this residual structure, and the confidence that it cannot be explained by errors in timing. catalog calibration, centroiding, or incomplete gravitational modeling. The first element of this definition is the choice of baseline model. A gravity-only baseline must be complete at the precision level in question. It includes the Sun and planets, uses accurate ephemerides accounts for light travel time and aberration, and uses consistent timescales and frames. If the baseline is incomplete, residuals can appear that are not physical. Therefore, a claim of acceleration is only meaningful relative to a specified baseline. If different baselines are used, the inferred acceleration can change. In careful work, the baseline is cross-checked by independent software and independent pipelines. Agreement across independent computations strengthens confidence that the residuals are not a computational artifact. The second element is realistic uncertainty. Each measurement has an uncertainty, and uncertainties are not always independent. Observations from the same telescope can have correlated errors due to shared systematics. If errors are correlated, residuals can look coherent, even when no physical acceleration exists. Therefore, analysts examine residual distributions and adjust weights to reflect real scatter. They also look for observatory-specific offsets. If one observatory dominates the residual drift, the drift may be systematic. If the drift persists across many observatories with different instruments and reduction methods, the case for a real effect strengthens. The statistical language here matters. A residual that is larger than the formal uncertainty is not necessarily significant if the formal uncertainty was underestimated. Significance must be judged against realistic error budgets. The third element is the pattern over time. A true additional acceleration produces a predictable kind of divergence. Over time, a constant acceleration produces a displacement that grows roughly with the square of elapsed time in a simple one-dimensional sense, though the observed sky projection can complicate this. A distance-dependent acceleration produces a divergence that changes as the object moves closer to or farther from the Sun. A time-variable acceleration, such as one linked to rotation or outbursts, produces residual patterns that can change more abruptly or show periodicity. Therefore, the residual time series is examined for smooth drift, for curvature for steps, and for periodic components. Steps and sudden changes often suggest data issues, catalog regime changes, blending events, or physical outbursts that would also affect brightness and morphology. Smooth drift suggests a continuous force or a stable systematic bias. Periodic components suggest rotation-dependent centroid shifts or forces. This definition also demands a separation between center of mass motion and center of light motion. The orbit model describes the center of mass. The astrometry measures a light centroid. If the light centroid is biased, residuals can appear even if the center of mass follows gravity perfectly. Therefore, the claim of acceleration must be accompanied implicitly or explicitly by evidence that the astrometry traces the nucleus. Such evidence can include point-like appearance in high-resolution images, minimal dependence of measured position on aperture size, and consistent results across different centroiding algorithms. Without these checks, the measured residual pattern could be an optical artifact of a dust coma or tail. When these elements are in place, the term accelerating can be quantified. Analysts may fit a non-gravitational acceleration term to the data. The fitted term is expressed as an acceleration vector in a chosen frame and may be scaled by a function of heliocentric distance. The fit returns parameter values with uncertainties. If the acceleration parameters are significantly different from zero and robust under different data subsets and reductions, the claim gains weight. Yet even then, the claim that there is no natural cause is still not justified. A measured non-gravitational acceleration is a natural phenomenon in small body dynamics. The correct question is which natural cause is consistent with the acceleration's direction, magnitude, and time dependence given physical constraints. The phrase "right now" is also examined. It implies contemporaneity and perhaps suddenness. In reality, most detected non-gravitational accelerations are inferred over an interval. The acceleration may be present continuously, but it becomes detectable only after enough time. A sudden detection can be the result of reaching sufficient arc length rather than a sudden onset of the force. Alternatively, the force could change due to an outburst. Distinguishing these requires looking for correlated changes in brightness and morphology. If the acceleration appears to turn on at a specific time, and if brightness changes or coma features appear, then a physical event is plausible. If no such changes exist and the acceleration appears as a steady drift, it is more likely a continuous effect that became measurable as the arc grew. This region also considers the possibility that the object's classification as unusual is being driven by language rather than by numbers. A small fitted acceleration might be statistically significant but physically modest. Its magnitude may fall within the range commonly observed for comets with weak activity. It may also be consistent with radiation pressure if the object is small. The way it is described in headlines depends on context, but the measured content remains the same. Therefore, the disciplined approach is to keep the discussion anchored to the acceleration's magnitude and direction, and to compare them to known ranges. Such comparison does not require speculation. It requires only knowledge of what similar objects exhibit. In orbit analysis, acceleration is also tested by forecasting. A fitted acceleration term should improve forward predictions. This is the most practical test because it asks whether the term captures a real, repeatable aspect of the motion. If the term improves fit to past data but fails to predict future positions, it may be overfitting or compensating for systematics. Therefore, the claim that an object is accelerating is strongest when the fitted model predicts new data well, and weakest when it is based solely on retrospective fitting. By the end of this region, accelerating right now has been reduced to a specific measurable claim, a robust, statistically significant residual pattern relative to a complete gravitational baseline, implying a non-zero additional acceleration term that persists across independent data sets and improves prediction. The claim there is no natural cause has not been supported by this definition. It has been postponed because the next inward step is to examine whether the residual pattern could still be produced by measurement chain vulnerabilities, and then to evaluate known natural mechanisms such as outgassing dust, centroid bias, radiation pressure, and thermal recoil. Only after those mechanisms are tested against the measured acceleration and against physical constraints can any statement about causes be made responsibly. The definition here is therefore not an answer, but a foundation, turning an emotionally loaded phrase into a concrete pattern that can be audited and explained within the ordinary framework of small body physics and careful measurement. With acceleration defined as a robust residual pattern against a specified gravitational baseline, the next inward step is to clarify what can and cannot be inferred from such a pattern. A measured acceleration is not a verdict. It is an output of orbit determination that depends on model assumptions, data weighting, and how the astrometry traces the object. Therefore, the phrase "accelerating right now" must be translated into a set of measurable statements, and the phrase "there is no natural cause" must be translated into a much narrower statement: no cause within the set of mechanisms already tested under the current constraints. The difference between these two translations is the difference between a claim and a conclusion. The measurable statements begin with the residuals themselves. Are the residuals coherent in time? Do they have a preferred direction? Do they scale with heliocentric distance or with viewing geometry? Do they persist when data subsets are changed? If a residual drift is seen only in one observatory's data, it is likely systematic. If it is seen across multiple observatories, it is more likely to be real or to reflect a shared bias, such as a catalog issue. If the drift aligns with the object's direction of motion, timing errors and along-track forces become candidates. If it aligns with the sun object direction projected on the sky, radiation pressure outgassing and dust centroid bias become candidates. If it changes direction over time, rotation-dependent effects and time-variable forces become candidates. These directional and temporal diagnostics are what the phrase "accelerating" must reduce to. The next measurable statement is the magnitude. A non-gravitational acceleration can be small but still significant. Significance is a statistical concept, but magnitude is a physical one. A modest acceleration might correspond to a small thrust that is common among weakly active comets. A larger acceleration might require either a very small mass, strong activity, or a strong centroid bias. Without size and mass constraints, magnitude alone can be misleading. Brightness does not uniquely determine size, because reflectivity is unknown and dust can dominate light. Therefore, any magnitude statement must be paired with a range of plausible sizes and densities and a recognition that the nucleus mass may be poorly constrained. A third measurable statement is the model dependence. Orbit fitting often uses standard parameterizations for non-gravitational forces. If one parameterization is used, an acceleration term may fit well. If a different parameterization is used, the inferred term may change. For example, an outgassing law that assumes water-driven sublimation may be inappropriate if activity is driven by more volatile substances. A radiation pressure model may assume a constant area-to-mass ratio that is not valid if the object is shedding dust. A thermal recoil model may assume stable rotation. If assumptions are wrong, the fitted acceleration can become a proxy for multiple effects. Therefore, the phrase "there is no natural cause" is at best a statement that no cause within a particular assumed model family has yet produced a fully satisfactory fit and prediction. The phrase "right now" is also a modeling statement. If the acceleration is inferred from a fit over a recent interval, it may reflect a change in data quality rather than a change in physics. As the object brightens, astrometry improves and residuals become smaller, making subtle effects detectable. Alternatively, as the object brightens due to dust, centroid bias can increase, making apparent acceleration larger. In both cases, the sense of a present acceleration can be an artifact of crossing a detectability threshold. The physical question is whether the inferred acceleration remains when the data set is extended and when different reduction choices are tested. At this stage, the tidal language must be held against the simplest counter-explanations. The most common counter-explanation for apparent acceleration is not exotic physics. It is measurement bias combined with the orbit's tightening. A second common counter-explanation is incomplete modeling of the measurement environment, such as differential chromatic refraction blending or catalog systematics. A third is that the fitted acceleration term is compensating for heterogeneous data sets with different systematic properties. Therefore, before any physical mechanism is judged, the residual pattern must be shown to survive these counter-explanations. This region also clarifies how a claim of no natural cause could ever be supported. In practice, it cannot be supported in an absolute sense, because natural causes include a wide range of known mechanisms and combinations, and because measurement is never perfect. The best that can be supported is a constrained statement such as, under the current data set and within realistic uncertainties, the residual drift cannot be explained by known observational systematics and is consistent with an additional acceleration whose magnitude and direction are not easily matched by standard outgassing radiation pressure or thermal recoil models given plausible physical parameters. Even that statement is a high bar and requires strong evidence. It also requires that plausible parameters be bounded by independent observations, such as thermal size constraints and spectral limits on gas production. Without such constraints, it is always possible that a natural mechanism with extreme but still physically possible parameters could produce the effect. Therefore, the inward move in this region is to locate exactly which constraints are missing. If size is unknown, radiation pressure cannot be bounded. If rotation state is unknown, thermal recoil cannot be bounded. If gas production is unconstrained, outgassing cannot be bounded. If morphology is unmeasured, centroid bias cannot be bounded. If catalog and refraction systematics are not tested, measurement artifacts cannot be bounded. The phrase "there is no natural cause" is thus revealed as shorthand for a large set of missing measurements. The disciplined response is not to accept the shorthand, but to specify which measurements would collapse the uncertainty. In a practical sense, the next steps are straightforward. Obtain high-resolution images to establish whether the object is point-like and to measure any coma or tail asymmetry. Measure astrometry with nucleus-focused methods and test aperture dependence. Obtain spectroscopy, or at least broadband color measurements, to constrain composition and to identify whether gas emission is present. Obtain thermal infrared observations, if possible, to constrain size and albedo. Gather a robust light curve to determine rotation period and to detect tumbling or spin changes. Extend the astrometric arc and test prediction with and without an additional acceleration term. Compare independent orbit solutions produced by different teams and software. Each of these steps reduces the room for ambiguous interpretation. By the end of this region, acceleration has been translated into a set of diagnostic questions rather than a rhetorical statement. The object either shows a robust residual drift or it does not. If it does, the drift has a direction, a magnitude, and a time dependence, that can be compared to known mechanisms. If it does not, the claim collapses. The phrase there is no natural cause is not accepted as a conclusion. It is reinterpreted as a description of a current modeling gap that is likely to be closed by improved constraints on size rotation activity and measurement biases. The next inward step is therefore not to escalate language. It is to build the gravitational baseline with maximum completeness, and then to examine residual patterns with a stricter audit of measurement chain vulnerabilities, because the most natural cause of unexplained acceleration in practice is that something in the measurement chain or in the modeling assumptions is not yet properly accounted for. A claim of unexplained acceleration becomes meaningful only after the gravity-only baseline is built with enough completeness that missing standard terms cannot plausibly produce the residual pattern. This region therefore returns to the baseline not to repeat earlier ideas, but to harden the reference against which any extra acceleration is measured. Gravity only here means the object is treated as a test mass influenced by the gravitational field of the solar system, and the observer is treated with the full set of geometric corrections required to map that motion into predicted sky positions. The purpose is to remove every ordinary source of mismatch that could otherwise be mistaken for an exotic effect. The gravitational field begins with the Sun, but the Sun is not stationary. The solar system's center of mass lies near the Sun, but not exactly at its center because planets tug on it. Therefore, precise orbit integration is often carried out in a barycentric frame. In that frame, both the object and the planets move according to a consistent set of equations and ephemerides. If a heliocentric frame is used, careful corrections must still ensure that the Sun's motion is accounted for. A mismatch between frames can produce small systematic errors. Such errors can appear as residual drifts, especially over long arcs. Therefore, gravitational completeness includes frame consistency and the use of precise planetary positions. Planetary perturbations are included using ephemerides that provide the positions and velocities of the planets over time. The influence of the planets is usually smaller than the Sun's, but it is not negligible, particularly when the object is in the inner solar system, where planetary distances can become relatively small. Even when there is no close approach, the combined tug of planets can shift the predicted sky position by an amount that becomes comparable to astrometric precision. If a planet is omitted or a poor ephemeris is used, residuals can develop that are not due to a real additional acceleration. Therefore, the baseline uses a full set of planets and a trusted ephemeris, and it tests sensitivity by comparing results under alternate ephemerides when possible. The baseline also includes relativistic corrections at the level required by the data. For many small body applications, Newtonian gravity is sufficient, but for high precision and for geometries near the Sun, relativistic effects can matter. These effects include both corrections to the object's motion in the Sun's gravitational field and corrections to light propagation. The correction sizes are modest, but the point is not their drama, it is their predictability. If such predictable effects are omitted, the orbit fit may compensate by introducing a spurious non-gravitational term. Therefore, including them is part of ensuring that any remaining acceleration term is not simply a placeholder for missing known physics. The observer model is just as important. Observations are made from specific points on Earth's surface and Earth rotates. The observatory's position must be transformed from Earth-fixed coordinates to an inertial frame at the time of observation. This transformation depends on Earth orientation parameters and on accurate time conversion. A systematic timing bias shifts the observer's position along Earth's rotation, which shifts the predicted line of sight. The effect is small, but can be coherent. Therefore, the baseline includes rigorous time standards and validates the timestamps for each observation set. In practice, one test is to examine whether residuals align with the direction of motion on the sky, and whether they scale with apparent angular speed, because timing errors often produce along-track residuals that scale that way. Atmospheric effects are not part of gravity, but they are part of mapping observed pixel positions into sky positions. Refraction shifts apparent positions toward the zenith, and the correction depends on pressure and temperature. Differential chromatic refraction depends on wavelength and on the object's color relative to reference stars. In many pipelines, approximate corrections are applied. If the object is observed at a high air mass, repeatedly refraction-related biases can be coherent and can mimic a non-gravitational effect. Therefore, a hardened baseline includes selection or weighting that reduces the influence of high air mass observations, and it tests whether the residual pattern changes when such observations are excluded. If the claimed acceleration disappears under that exclusion, the cause is not dynamical. Catalog systematics also sit at the boundary of baseline completeness. Astrometric reduction relies on reference star catalogs. If the catalog has local biases, those biases can imprint on the measured positions. In a hardened analysis, one checks whether residual patterns correlate with sky region and whether re-reducing data using a different catalog changes the result. If different catalogs yield different inferred accelerations, the acceleration may be at least partly catalog-driven. If the effect persists across catalogs, confidence increases that it is real or that it reflects a bias common to both catalogs. Once the gravity-only baseline is hardened, the orbit solution should become predictive. The object's next positions can be forecast with a small uncertainty region. This allows the cleanest test of an additional acceleration. If the object is observed at the forecast times, and the observed positions consistently land off-center in the same direction, then either a real additional acceleration exists, or a persistent bias exists. The distinction then hinges on whether the bias can plausibly remain stable across different observing systems. If multiple observatories with different optics detectors and pipelines see the same offset, a shared bias becomes less likely. If only one observatory sees it, a localized bias is likely. In this region, the phrase "no natural cause" is reinterpreted as a statement about what remains after hardening. If residual drift remains after the baseline includes full planetary perturbations, relativistic corrections, where relevant rigorous time and frame handling and careful selection against refraction and catalog-driven systematics, then the residual is more likely to be physical, in the sense of either a real non-gravitational acceleration or a center-of-light bias tied to the object's own environment. Both of these are natural. Therefore, the phrase "no natural cause" is still not justified. The only change is that the space of plausible explanations becomes narrower, and attention can move more confidently to physical mechanisms that are external to gravity such as outgassing and light-driven forces, and to the optical effects of dust and coma. A crucial practice here is cross-validation with independent orbit determination. Different software uses different numerical integrators, different default models, and different ways of handling uncertainties. If independent solutions agree on the presence and direction of a residual drift, confidence increases that it is not a coding artifact. If they disagree, the claim of acceleration is weakened. Similarly, independent teams may handle data weights differently. If the acceleration depends strongly on one team's weighting scheme, it may be an artifact of how the data were treated. A hardened baseline therefore includes sensitivity tests, remove suspect data, vary weights, compare catalogs, and compare software. A real acceleration should survive these stresses and remain within similar ranges. By the end of this region, the stage is set for the next inward step, which is to examine the measurement chain failure modes in detail as they apply specifically to this object's dataset. The hardened gravitational baseline narrows the question. If an acceleration is still inferred, it is either because the object experiences a non-gravitational force, or because the measured centroid is shifted by dust or other brightness structure. The next step is therefore not to proclaim a lack of natural cause, but to systematically audit the non-gravitational and observational pathways that are known to produce precisely these kinds of residual patterns, beginning with the simplest and most common subtle biases in astrometry due to centroiding blending and the object's own extended emission. Only after those are tested can the physical force mechanisms be evaluated with confidence. With the gravitational baseline hardened, the residual pattern becomes the central object of study, and its significance depends on whether it survives the most stringent tests of data robustness. Residuals are not treated as a single number, but as a field. Each observation has a residual vector on the sky, and the collection of vectors can reveal structure. The first question is whether the residuals are centered around zero. If they are not, there is a bias. The second question is whether the bias is stable in time and direction. If it is, it can be parameterized as an additional acceleration or as a stable measurement offset. The third question is whether the bias appears across independent datasets. If it does, it is less likely to be a localized error. The outcome of these questions is not an interpretation yet. It is a classification of the residual behavior. A coherent residual drift can take several forms. It can be a smooth divergence that grows with time. It can be a near constant offset that persists. It can be a drift that changes slope. It can be a pattern that repeats with a period. Each form suggests different tests. A smooth divergence that grows steadily is consistent with an unmodeled continuous acceleration or with a systematic error that is stable in sign. A constant offset is consistent with a stable astrometric bias, such as a catalog offset, a timing offset, or a persistent centroid shift in the same direction. A drift that changes slope could indicate a change in force magnitude with solar distance, a change in object activity, or a change in observing conditions or instruments. A periodic residual suggests rotation-linked effects, either in the force itself or in the measured center of light. The data can be subdivided to probe these possibilities. One subdivision is by observatory. If the drift is dominated by one site, it is likely instrumental or reduction-related. If the drift is present in multiple sites, But with different amplitudes, it may still be systematic, because different pipelines can respond differently to the same extended structure. If the drift is consistent across sites, it points toward a common physical cause, or a shared bias such as catalog systematics. Another subdivision is by time. If the drift is present only early on and fades later, it may reflect early low signal-to-noise astrometry or early blending events, not a persistent force. If it begins at a certain time, it may reflect a physical change, such as an outburst, or a change in geometry, such as the object entering a crowded field. Another subdivision is by observing geometry. Residuals can be examined versus air mass to test refraction effects, versus phase angle to test scattering and dust geometry, and versus sky region to test catalog variations. Another crucial robustness test is to vary the reduction method. Astrometry relies on assumptions about the point spread function and the background. A faint object can be centroided by fitting a symmetric function, by using a weighted centroid, or by fitting a trailed model if motion during exposure is significant. Each method can yield slightly different positions when the object is faint or extended. If the inferred acceleration depends strongly on the centroiding method, it is likely that the object's light distribution is influencing the measurement. If it is insensitive to method, the measurement is more likely tracing a stable physical point. A similar test concerns aperture dependence. If the object has a coma or tail, the measured centroid can shift as the aperture includes more extended light. A small aperture may emphasize the nucleus. A larger aperture includes more coma and tail. If measured positions shift systematically with aperture, then the center of light is not coincident with the nucleus. This can create apparent acceleration because the centroid shifts in a direction often related to the sun object line, since tails tend to point away from the sun. Therefore, a claim of non-gravitational acceleration is weakened if aperture dependence is strong and is strengthened if aperture dependence is minimal. Blending is tested through image inspection and through cross-matching with background catalogs. The object can pass near faint stars and galaxies that are below easy visual detection in single exposures. When overlap occurs, the centroid can be pulled toward the background source. If this occurs on some nights and not others, it creates residual outliers and can bias the orbit if not recognized. If the object's path crosses crowded regions, blending becomes more likely. A robust analysis flags exposures with potential blends and either corrects them or downweights them. If the acceleration signal is driven by a small number of such exposures, it is not a real dynamical effect. If the signal persists after those exposures are removed, it gains credibility. Timing consistency is also tested through residual direction. Timing errors tend to produce along-track residuals that scale with apparent motion rate. If residuals are predominantly along the direction of motion, and the magnitude scales with the motion rate, timing becomes a leading suspect. If residuals are not aligned with motion or do not scale, timing is less likely. Timing problems can also be isolated by comparing exposures taken close in time with different timing systems or by checking the metadata. In a multi-observatory data set, it is common for a single timing misconfiguration to create a stable offset. Catalog-related biases can be probed by re-reducing data with alternate catalogs, or by comparing residuals of other objects measured in the same fields. If many objects show similar offsets in a field, the field solution or catalog may be biased. If only this object shows the offset, the cause may be the object's morphology or a force. Catalog bias can also produce systematic differences in right ascension versus declination residuals, depending on local distortions. Such patterns can be diagnostic. If after these tests, a coherent drift remains a parameterized acceleration model, can be fit and evaluated by its predictive power. The acceleration parameters are not accepted because they reduce residuals retroactively. They are accepted only if they improve forecasting. This involves holding out part of the data or using new observations obtained after the fit. If the acceleration model predicts those new observations better than the gravity-only model, the acceleration is likely capturing a real effect. If it fails, the model may be fitting noise or systematics. Predictive validation is the strongest method available in this context because it does not rely on subjective judgments about residual plots. It relies on whether the model can point a telescope correctly. At this point, the phrase "no natural cause" becomes even more constrained. If the acceleration model is predictive and robust, the question is not whether there is a natural cause. The question is which natural mechanism matches the acceleration vector and magnitude within physical constraints. An acceleration that is strongly radial and scales with solar distance invites radiation pressure and outgassing. An acceleration that is a long track invites thermal recoil and directional outgassing. A time-variable acceleration invites episodic activity rotation dependence or evolving dust environments. The residual classification and the robustness tests determine which of these are plausible. This region therefore acts as a filter. It either reveals that the acceleration claim is not robust, collapsing under method changes, aperture changes, observatory subdivision, or the removal of blended exposures. Or it reveals that the claim survives and can be expressed as a quantified acceleration term that improves prediction. Only in the second case does it become sensible to proceed inward to physical mechanisms with confidence. Even then, the next step is not to deny natural causes. It is to examine the measurement chain again through the lens of the object's own environment, because dust and subtle coma can survive even in point-like images and can bias astrometry in ways that mimic physical accelerations. Therefore, the next inward step focuses on the measurement chain failure modes most relevant to a small body that may release dust and gas, and then on outgassing as the standard natural thrust mechanism that often explains persistent residual drift. Even when residuals appear robust across basic subdivisions, the measurement chain can still create a persuasive illusion of acceleration through a small number of persistent object-specific effects. These effects are not generic instrument flaws. They arise from the interaction between the object's faint light and the methods used to turn that light into a coordinate. Because an apparent acceleration is often small, it can be produced by subtle biases that remain stable in sign over time. This region therefore focuses on those object-specific pathways, beginning with the simplest, the fact that the astrometric measurement is usually tied to the center of light, not the center of mass. If the object is perfectly point-like, and its light distribution is symmetric, the center of light and the nucleus location coincide within noise. If the object has even a slight coma, the light distribution can become asymmetric. Dust tends to be pushed away from the sun, creating a tail or an asymmetric coma that points anti-sunward. Gas can also create structures such as jets, but dust dominates the visible brightness in many cases. An asymmetric dust distribution can shift the center of light by a small fraction of the point spread function. This shift can be smaller than what is obvious by eye, especially when the object is faint. Yet a shift of that scale can be large enough to create a coherent residual drift over weeks. Importantly, the shift can remain aligned with the sun object direction, because the dust asymmetry tends to align with that direction. This makes the resulting residual pattern resemble a radial acceleration away from the sun, which is also the signature expected from radiation pressure, or anti-sunward outgassing. Therefore, dust centroid bias is a central confounder. The magnitude of centroid bias depends on the measurement method. A pipeline that fits a symmetric point spread function may return a centroid closer to the brightest inner region, which may be nearer the nucleus. A pipeline that computes a weighted centroid over a larger region may include more tail light and shift the centroid further. Seeing changes alter how much of the coma is blended into the core. A night with poor seeing can smear the dust into the core and increase centroid bias. A night with good seeing can separate the core and reduce bias. If seeing conditions vary systematically over time, perhaps due to seasonal weather patterns at a given site, a spurious drift can appear. Even if seeing varies randomly, it can create scatter that might be mistaken for time-variable acceleration. Therefore, one of the strongest tests is to measure positions with different aperture sizes and different centroid methods, and to check whether the inferred acceleration changes. Another object-specific pathway is color. Differential chromatic refraction shifts the apparent position of a source depending on its spectral energy distribution. Reference stars have a distribution of colors. The object may have a different color, especially if its light is dominated by dust scattering or by gas emission bands in certain filters. At higher air mass, the atmosphere's refractive index causes a color-dependent shift. The shift is typically along the zenith direction. If the object is observed repeatedly at similar air mass and similar hour angles, this shift can be coherent. If the object remains visible only in a narrow time window near dawn or dusk, such repetition is common. The resulting residual pattern can mimic a stable offset or a drift, depending on how the observing geometry changes over time. This bias can persist across observatories if they observe at similar air mass windows, making it look like a global effect. Testing requires multi-filter astrometry, or at least comparing residuals across different filters and air mass ranges. Trailing and motion during exposure can also become object-specific. If the object's apparent motion is non-negligible, even small trailing can bias centroid estimates. Different observatories use different exposure times. A longer exposure increases signal-to-noise, but increases trailing. A shorter exposure reduces trailing, but reduces signal-to-noise. The trade-off can produce different centroid biases across data sets. If the object's apparent motion changes over time, as it often does with changing distance, the amount of trailing changes even for fixed exposure time. This can create a time-dependent systematic shift that might be mistaken for acceleration. The test here is to examine residuals as a function of exposure time and apparent motion rate. If residual magnitude correlates with these trailing related centroid bias is implicated. Background complexity was another object-specific factor. A faint object moving through a dense star field or near a galaxy background can suffer from subtle blending that is not flagged as a clear overlap. The background can be uneven and the centroid algorithm may be pulled by gradients. This can create systematic biases if the background structures are persistent along the object's path. If the object moves into a cleaner field later, the bias can change, producing a step or a drift. Such changes can be misread as a change in acceleration. The test is to inspect image cutouts and to map residuals onto sky position to see whether residual changes coincide with entering or leaving crowded regions. There is also a subtle object-specific bias associated with signal-to-noise itself. At low signal-to-noise centroid estimates can be biased toward brighter noise fluctuations in the vicinity of the true centroid. This bias is not purely random. It can have directionality if the point spread function is asymmetric or if the background is sloped. If the object is near the detection threshold in early data and becomes brighter later, the centroid bias can change with time, creating an apparent drift. This is a common pathway to a headline claim: early data points, noisier and more biased, pull the orbit. Later data points, cleaner, reveal a mismatch. The mismatch is then interpreted as acceleration. In reality, the mismatch may be a change in measurement quality. The robust approach is to reweight early data appropriately, or to restrict the analysis to high-quality data and see whether the acceleration remains. An additional pathway is the choice of catalog and the density of reference stars. In sparse star fields, the astrometric solution can be less constrained, and small distortions can produce offsets. In dense fields, the solution can be more constrained, but also more vulnerable to mismatches and to unresolved binaries in the catalog. If the object's observations occur across varying star densities, the quality of the astrometric calibration can vary. This can produce time-varying residual behavior that mimics acceleration. Testing includes comparing residuals to the number of reference stars used and to the quality metrics of the plate solution. When these object-specific pathways are considered together, the phrase "no natural cause" becomes less tenable because many of these pathways produce acceleration-like residuals without any change in the object's center of mass motion. They are natural in the sense of being expected consequences of measuring faint, potentially extended sources. They are also testable. A careful analysis can attempt nucleus-centered astrometry by fitting a model that includes a coma component and solving for the nucleus position. It can use high-resolution images to locate the photocenter relative to coma structure. It can compare positions in different filters and at different air masses. It can examine residual dependence on aperture seeing exposure time and background field. Each test can either reduce the apparent acceleration or demonstrate that it is insensitive to these choices. If after all these tests the residual drift remains, then the object is either experiencing a real non-gravitational acceleration, or there is a shared systematic bias that has not been identified. At that point, physical mechanisms become the focus, beginning with outgassing, because outgassing is the most common natural source of measurable non-gravitational acceleration in small bodies. The movement inward is therefore justified only when the measurement chain has been shown to be stable with respect to method choices. Otherwise, the acceleration is not a property of the object. It is a property of the way the object's light is turned into a coordinate. This region aims to make that distinction sharp because it is the central difference between an object that is truly accelerating and an object that is merely difficult to measure. If the acceleration, like residual drift, survives a strict measurement audit, the next inward step treats it as potentially dynamical and evaluates the most established natural mechanism for such drift, non-gravitational thrust from outgassing. Outgassing is the momentum exchange that occurs when volatile material transitions from solid to gas and escapes the surface. The escaping gas carries momentum away from the nucleus. Conservation of momentum requires an equal and opposite reaction on the nucleus. The resulting acceleration can be small, but it can be measurable because it acts continuously, and because modern astrometry can detect small, systematic divergences from gravity-only predictions when the arc is long and the data are good. Outgassing is driven by solar heating, but the relevant temperature thresholds depend on which volatile substances are present and where they are located. Water ice requires relatively warmer conditions to sublimate vigorously, while more volatile substances can sublimate farther from the sun. The surface may be covered by a porous dust layer that insulates underlying ice. Heat can penetrate slowly, and this creates delays. Cracks and vents can expose fresh material and allow gas to escape through localized jets. Because activity can be localized, the thrust can have a preferred direction. A perfectly symmetric, evenly active surface produces little net thrust because forces cancel. A localized jet produces a net thrust that can be large compared to the object's mass, especially if the object is small. The direction of thrust is decisive for interpreting residuals. A simple expectation is that the thrust is roughly away from the sun because the sunward side is warmer. Yet real bodies introduce a thermal lag. The warmest region can occur on the afternoon side of the rotating body offset from the subsolar point. Therefore, the average thrust vector in space can be rotated relative to the sun object line. In orbit coordinates, this can produce components not only radial, but also along track, changing the object's speed along its orbit and sometimes out of plane if the jet geometry is tilted. This means that a measured residual pattern that is not purely radial does not rule out outgassing. It can instead indicate a rotated thrust direction set by rotation, thermal inertia, and jet location. Outgassing also varies with time. As the object approaches the sun, heating increases and activity can rise. As it recedes, activity can fall. Yet many objects show asymmetry around perihelion because heat penetration and surface evolution delay peak activity. Therefore, the acceleration can be stronger after perihelion than before, or vice versa, depending on surface properties. Over the limited arc of observations, a changing outgassing acceleration can appear as a drift whose slope changes. If residuals show such curvature in time, outgassing with distance-dependent scaling becomes plausible. If residuals show a step-like change, an outburst or a sudden exposure of fresh ice becomes plausible. In each case, the dynamical signature is linked to a physical change, rather than to an unexplained effect. Evaluating outgassing requires connecting the inferred acceleration to plausible gas production rates. The acceleration implies a required thrust. Thrust is roughly the product of gas mass flow rate and gas outflow speed, adjusted for collimation and directionality. Gas outflow speeds depend on temperature and molecular weight, and are typically on the order of hundreds of meters per second for common cometary gases. The nucleus mass depends on size and density. Size may be uncertain because brightness can include dust, and density is uncertain because small bodies range from porous aggregates to more consolidated fragments. Therefore, this evaluation is done in ranges. Analysts ask whether within plausible size and density ranges, the required gas production is consistent with what would be observable and with what is typical for small bodies at the object's solar distance. This is where observation constraints matter. If spectra show clear gas emission, outgassing becomes strongly supported. If spectra show no emission, outgassing is not ruled out, but production rates are constrained by upper limits. If the required production rate exceeds these limits by a large margin, outgassing becomes less likely as the main cause. If the required production is below limits, it remains plausible. Photometric behavior also matters. A growing coma or an increasing brightness beyond what distance and phase angle alone would predict supports activity. Yet a dust-poor gas flow can produce thrust with minimal visible dust, especially if the gas production is low and if dust release is limited. Therefore, absence of a dramatic coma does not eliminate outgassing, but it requires more careful constraint. Outgassing is intertwined with dust and with measurement bias. The same jets that provide thrust can also create asymmetric brightness. An asymmetric coma can shift the center of light. The measured astrometry can then be biased in a direction related to the jet and tail. This can mimic or amplify the dynamical signal. It can also partially cancel it depending on geometry. Therefore, outgassing as a dynamical cause cannot be evaluated purely from astrometry. It must be evaluated alongside morphology. If the direction of inferred acceleration matches the direction of observed asymmetry, there are two possibilities. One is that the asymmetry indicates a jet that produces thrust in that direction. The other is that the asymmetry is producing a centroid bias that is being interpreted as thrust. Distinguishing these requires nucleus-centered astrometry and high-resolution imaging. Outgassing models used in orbit fitting often employ parameterized acceleration components scaled by a function of heliocentric distance. These functions are approximations. They are designed to mimic sublimation behavior of common volatiles. If the object's composition differs, the scaling may differ. If activity is driven by exposure of fresh patches rather than by a uniform surface, scaling may differ. Therefore, a poor fit does not necessarily mean outgassing is absent. It may mean the parameterization is too simple. Conversely, a good fit does not necessarily mean outgassing is the only cause. It may mean that a smooth acceleration term is approximating a combination of physical thrust and centroid bias. This is why predictive validation remains essential. If an outgassing-like acceleration model predicts future positions better than a gravity-only model, it indicates that a systematic effect exists and is stable enough to forecast. Whether that systematic effect is true thrust or stable centroid bias still requires morphological checks, but the predictive success is a strong sign that the residual pattern is not random. If the headline says, "There is no natural cause," outgassing is the first and most likely natural cause to test because it has a long record of explaining non-gravitational accelerations in comet-like bodies. The correct posture is to assume it is possible until evidence rules it out. Evidence that disfavors outgassing includes a lack of any detected coma or tail in deep imaging strict spectral upper limits that are incompatible with the required production rates, and an acceleration direction or scaling that is inconsistent with plausible jet geometry and solar heating. Even then, a small amount of outgassing could still be present, but not dominant. In such cases, other mechanisms like radiation pressure and thermal recoil are considered, and the possibility of purely observational centroid bias is revisited. At the end of this region, outgassing stands not as a dramatic explanation, but as a default physical hypothesis that connects the measured acceleration to solar heating, to composition, and to surface structure. It provides testable predictions. If outgassing is the driver activity, indicators should correlate with the inferred acceleration. Brightness and morphology may change in ways consistent with increased gas and dust release as solar distance decreases. Acceleration magnitude may scale with distance. If these correlations do not appear, outgassing becomes less persuasive. The analysis then proceeds inward to sunlight-driven forces on mass and on dust, because even in the absence of detectable outgassing, photons can provide acceleration directly through radiation pressure, and heat can provide acceleration through thermal recoil. Each mechanism has its own constraints, and each is natural in the strict physical sense, even when it produces motion that feels surprising to casual description. If outgassing cannot fully account for the inferred acceleration, or if constraints on gas production make it unlikely as the dominant cause, sunlight becomes the next inward mechanism to examine. Sunlight is not only illumination, it is a stream of photons carrying momentum. When photons strike an object and are absorbed or reflected, momentum is transferred, producing radiation pressure. For most large bodies, this pressure is negligible compared to solar gravity. For small bodies with high area relative to mass, the resulting acceleration can be measurable. This mechanism is natural, well understood, and routinely included in models for dust grains and for some small artificial objects. The question here is whether it can plausibly act on the nucleus of 3I Atlas at the magnitude implied by the residual drift given plausible size and mass ranges. Radiation pressure acceleration depends on heliocentric distance through the intensity of sunlight, which decreases with the square of distance. It also depends on the object's effective cross-sectional area presented to the sun and on its optical properties such as reflectivity and how efficiently it absorbs. The acceleration is inversely proportional to mass. Therefore, the same apparent brightness can correspond to very different radiation pressure accelerations, depending on whether the brightness comes from a large, massive nucleus or from a small, low-mass nucleus surrounded by dust that enhances its light. This is why size constraints are critical. A faint object with a modest inferred acceleration could be consistent with radiation pressure if it is small enough. A brighter object with the same acceleration might require an implausibly low mass for its brightness, unless the brightness is dominated by dust. A key complication is that visible brightness is an uncertain proxy for size. The brightness depends on distance to the Sun and Earth, on phase angle, and on albedo. Two objects of the same size can differ greatly in brightness if their albedos differ. Dust can increase brightness dramatically, without increasing nucleus mass. Therefore, to evaluate radiation pressure, analysts seek independent size constraints, often from thermal infrared measurements. Infrared emission depends on how much heat the object radiates, which relates more directly to size than reflected light does. If thermal data constrains size, then mass can be estimated within a density range, and radiation pressure acceleration can be bounded. If thermal data are not available, the evaluation must use broad ranges and remain cautious. Radiation pressure also leaves a signature in the direction of the inferred acceleration. The force acts roughly away from the Sun, producing a predominantly radial acceleration in heliocentric coordinates. In the sky plane residuals, this radial acceleration projects into a direction that depends on geometry. If the inferred acceleration direction is consistently aligned with the projected anti-sunward direction, radiation pressure becomes more plausible. If the inferred direction is strongly along track or out-of-plane, radiation pressure alone becomes less likely, though it can still contribute in combination with other forces. Yet direction inference itself depends on the orbit fit and on the data, so it must be treated as a model-dependent output. Still, direction provides a valuable filter. Even if radiation pressure on the nucleus is too weak, sunlight can produce an apparent acceleration through its action on dust. Dust grains released from the nucleus have extremely high area-to-mass ratios and are strongly affected by radiation pressure. This is why tails form and why tail orientation tends to be anti-sunward. If a dust coma or tail dominates the light, the measured centroid can be pulled away from the nucleus in a direction related to the tail. That centroid bias can mimic a radial acceleration because it shifts the measured position in the anti-sunward direction. Unlike true nucleus acceleration, this bias depends on observing conditions and on measurement choices. It can change with seeing, with aperture size, and with filter. Therefore, in the radiation pressure region, the parallel question is not only whether photons push the nucleus, but also whether photons shape a dust environment that biases the measurement. The dust pathway has its own predictable dependencies. As the object approaches the Sun, dust production may increase, and radiation pressure will act more strongly on newly released dust. The dust distribution can become more extended, and the tail can become brighter relative to the nucleus. The center of light can shift. Phase angle affects scattering. In some geometries, forward scattering can make dust much brighter when viewed at small scattering angles, producing apparent brightening without a change in dust production. This can change the dominance of dust in the measured light, and therefore change centroid bias. As a result, an apparent acceleration might correlate with phase angle rather than with heliocentric distance, which would suggest a measurement bias rather than a dynamical force. Testing requires examining residuals versus phase angle and comparing observations in different filters because dust scattering and gas emission respond differently with wavelength. If radiation pressure on the nucleus is being considered seriously, the inferred area-to-mass ratio must be checked for plausibility. Natural small bodies have densities and structures that limit how low their mass can be for a given size. A very porous aggregate could have a low density, but there are still limits. If the inferred area-to-mass ratio implies an extremely low density or an extremely thin structure, the radiation pressure explanation becomes strained unless independent evidence supports such a structure. This evaluation does not require speculation. It requires comparing the inferred ratio to ranges seen or expected for natural bodies with appropriate humility about uncertainty. If the inferred ratio is within plausible bounds, radiation pressure remains viable. Radiation pressure also implies a smooth and continuous acceleration that scales with solar distance. If the inferred acceleration varies in a way that does not follow this scaling, radiation pressure alone is less persuasive. Yet again, dust can complicate this, because dust production can change, altering the measured centroid, and the centroid bias need not follow a simple inverse square law. Therefore, if the acceleration appears time variable, it may point back to dust and measurement. This is why, in practice, radiation pressure on the nucleus and dust-induced centroid bias must be evaluated together rather than separately. Both are sunlight-driven, but one is dynamical and one is observational. In the language of the title, the claim that there is no natural cause often arises when common expectations about gravity-only motion are violated. Radiation pressure is a natural cause that violates those expectations for sufficiently small bodies. It does not violate physics. It is physics. The challenge is to determine whether the object is in the regime where it matters, and whether the astrometry traces the nucleus. If the object is small and inactive, and if imaging shows it is point-like, radiation pressure can become a strong candidate. If the object is active and dusty, the dust centroid bias becomes a stronger candidate than direct radiation pressure on the nucleus, and any inferred acceleration must be interpreted with that in mind. At the end of this region, the analysis moves inward again toward thermal recoil, because even if radiation pressure is insufficient or ambiguous, absorbed sunlight and delayed thermal re-emission can produce a recoil acceleration tied to rotation and surface properties. Thermal recoil can produce a long-track drift that radiation pressure cannot easily mimic. It also provides a pathway for a natural cause in cases where the object appears inactive and point-like, and yet shows a small systematic divergence. Thus, the next inward layer addresses heat rotation and the subtle ways that energy balance can produce momentum exchange without gas and without dust dominance, completing the standard set of natural mechanisms that can explain non-gravitational accelerations in small bodies when measurement artifacts have been minimized. If sunlight pressure and outgassing remain insufficient or too degenerate with dust-induced biases, thermal recoil becomes the next inward mechanism, because it can produce a systematic acceleration even when the object appears inactive and point-like. Thermal recoil arises from anisotropic emission of infrared radiation. Sunlight heats the surface. The surface re-emits that energy as thermal photons. Those photons carry momentum. If emission is not symmetric in direction, the net momentum carried away produces a recoil force on the body. The asymmetry is created by thermal inertia, surface roughness, and rotation. This mechanism is not exotic. It is a standard contributor to the long-term evolution of small asteroid orbits, and its direction and magnitude are tied to physical properties that can in principle be constrained. The starting point is the daily cycle of heating and cooling on a rotating body. A point on the surface warms when sunlight strikes it, then cools after it rotates into darkness. If the surface responded instantly, The warmest point would coincide with local noon, and emission would be symmetric about the sunward direction, producing little net along-track recoil. In reality, materials store heat. Thermal inertia causes a delay. The warmest region shifts toward the afternoon side. When the warm afternoon region emits infrared radiation, the recoil has a component that can be aligned with or against the direction of motion along the orbit depending on the sense of rotation. This is the diurnal component. It tends to change the semi-major axis over time, slowly shifting the orbit. In an astrometric residual pattern over weeks or months, it can appear as a persistent drift that is not purely radial. The seasonal component depends on the tilt of the spin axis. If the axis is tilted, one hemisphere can be heated more over part of the orbit. Heat can be stored and re-emitted, later producing a recoil that can have a different direction. The seasonal effect can be important for some spin states and sizes. The combined thermal recoil is therefore sensitive to the rotation period spin axis, orientation, thermal inertia, surface roughness, and albedo. For a newly discovered faint object, many of these are unknown. The analysis proceeds by asking whether plausible ranges of these parameters can produce an acceleration of the magnitude inferred from residuals and in the direction suggested by the residual pattern. Magnitude constraints are grounded in energy balance. The maximum available energy is the absorbed sunlight. Absorbed power equals solar flux at the object's distance times the effective area times the absorbed fraction. The recoil force from thermal emission cannot exceed what is implied by that power, because each photon carries momentum equal to its energy divided by the speed of light. A perfectly collimated thermal emission in one direction would maximize recoil, but real surfaces emit broadly. Therefore, the recoil is a fraction of the absorbed power divided by the speed of light. This provides an upper bound. If the inferred acceleration would require a recoil larger than this bound, given plausible size, and albedo thermal recoil is ruled out. If it falls well below the bound, thermal recoil remains plausible. The size dependence appears again. Thermal recoil acceleration scales roughly with area-to-mass ratio, so smaller bodies with lower mass per area experience larger accelerations. Yet extremely small bodies may also have low thermal inertia due to their small size, and can equilibrate quickly, reducing thermal lag, while larger bodies may store heat and produce a stronger lag. There's an intermediate range where the effect can be strongest. Without a direct size estimate, thermal recoil cannot be pinned down. Therefore, brightness thermal observations, if available, and constraints on albedo become important. If the object's size is constrained to be too large, thermal recoil may be too weak. If it is constrained to be small, thermal recoil becomes more viable. The direction of thermal recoil is a powerful discriminator. A purely radial acceleration away from the sun is more naturally produced by radiation pressure or outgassing. Thermal recoil often produces a significant along-track component because the afternoon thermal lag is tied to rotation relative to orbital motion. If residuals indicate an along-track drift, thermal recoil becomes attractive. However, residual direction inference requires an orbit frame interpretation, and dust centroid bias can still complicate the sky plane direction. Therefore, in practice, analysts fit a thermal recoil-like acceleration component and test whether it improves prediction and whether the fitted component aligns with plausible spin states. This brings rotation into focus. Thermal recoil depends on spin period and axis. Photometric monitoring can reveal rotation period through brightness variations. A stable repeating light curve suggests a principal axis rotation and makes thermal recoil modeling more meaningful. A complex, non-repeating light curve suggests tumbling, which can reduce the net recoil by averaging emission over many orientations, or can create time-variable recoil. If the object tumbles, a simple constant recoil model may not fit well. Residuals might show variability or periodicity. Therefore, assessing spin stability is essential to deciding whether thermal recoil is a plausible dominant mechanism. Surface roughness also matters because it changes the angular distribution of emitted radiation. Rough surfaces have facets that can emit preferentially in certain directions and can create self-heating where one facet warms another. This can enhance or alter the net recoil. A very smooth surface emits more symmetrically. A very rough surface can create stronger anisotropy. Yet roughness is hard to measure directly. It is usually treated as a parameter range constrained indirectly by thermal infrared observations that probe how the surface heats and cools. Without such data, roughness remains a source of uncertainty that limits how strongly thermal recoil can be asserted. Thermal recoil also interacts with surface evolution. As the object approaches the sun, surface temperatures increase and can change the surface. Dust can migrate, exposing different materials and changing thermal inertia. Small fractures can form. Even weak outgassing can loft dust and alter the insulating layer. These changes can modify the thermal recoil over time. Therefore, a residual drift that changes gradually with time could still be consistent with thermal recoil if surface properties evolve. Conversely, a sudden step in residuals would be less consistent with thermal recoil alone, unless it coincides with a sudden surface change event. Again, correlations with photometry and morphology become important. A critical difference between thermal recoil and outgassing is that thermal recoil does not necessarily produce a visible coma. It can operate on inert bodies. Therefore, in cases where imaging shows no extended structure and spectra show no gas, thermal recoil becomes one of the primary natural explanations for a small measured acceleration. The evaluation then hinges on size and spin constraints, and on whether the inferred acceleration direction and scaling are compatible with thermal recoil expectations. In the language of the title, a claim that there is no natural cause often arises when the object appears inactive and yet seems to diverge from gravity-only predictions. Thermal recoil offers a natural cause precisely for that scenario. It depends on sunlight and heat, not on gas. It is subtle, and therefore can be overlooked by casual reasoning. Yet it is predictable in the sense that it must obey energy constraints and should correlate with rotation and solar distance in specific ways. These constraints allow it to be tested. By the end of this region, thermal recoil stands as a candidate mechanism that links the inferred acceleration to the object's physical properties. It is not asserted as the answer. It is placed within a testable framework. If thermal recoil is responsible, then improved constraints on size, albedo, spin state, and thermal inertia should narrow the inferred recoil and improve prediction. If such constraints rule it out, attention shifts to more complex combinations of forces, to time-variable activity, or back to residual measurement biases that may persist even in point-like images. The next inward step therefore focuses directly on rotation state, because rotation is the gatekeeper for whether outgassing thrust and thermal recoil average into a steady acceleration or vary in ways that can make the motion appear puzzling under simple models. Rotation and shape form the next inward layer, because they determine whether any non-gravitational mechanism produces a steady, predictable acceleration or a variable, hard-to-model disturbance, and because they also determine whether astrometry traces a stable point or a moving brightness distribution. A small body is rarely spherical. It is often elongated, irregular, and covered with facets. As it rotates, the projected area and illumination change, and its brightness changes. These brightness variations can be used to infer rotation period, but they also reflect the object's shape and surface heterogeneity. The same physical features that create a light curve also create anisotropies in heating and in potential gas release, which in turn create thrust and recoil forces. Therefore, rotation is both a diagnostic and a driver. A stable rotation in principal axis mode produces a repeating light curve. The period can be measured if observations cover enough cycles and if the signal is not drowned by noise or by changing viewing geometry. The amplitude of the light curve provides hints about elongation, though surface albedo variations can also contribute. If the object is tumbling, the light curve may not repeat cleanly. It may show multiple periods or irregular changes. Tumbling is important because it can average out directional forces. A jet that would produce a steady thrust in a stable rotation state can become time variable in a tumbling state, reducing net acceleration or changing its direction unpredictably. Thermal recoil can also be reduced by tumbling because the temperature pattern is not locked to a stable rotation axis. Therefore, if a measured acceleration appears stable over time, it suggests either a stable rotation state or a mechanism that is not strongly sensitive to rotation orientation, such as radiation pressure on the nucleus. If the measured acceleration appears to vary, rotation-dependent mechanisms become more plausible. Rotation is not fixed. Torques can change it. Outgassing jets can exert torque if their line of action does not pass through the center of mass. This is common on irregular bodies. Radiation pressure can also exert torque on irregular shapes and can change spin state over time. These torques can spin an object up or down and can change its spin axis orientation. If the spin changes during the observation arc, the direction and magnitude of outgassing thrust and thermal recoil can change, producing time-variable acceleration. This can create residual patterns that are not well fit by a constant acceleration model and can tempt an observer to declare a lack of natural cause. In reality, the cause would be natural but time-variable and coupled to a changing spin state. The coupling between rotation and measurement is equally important. If the object has a jet or an asymmetric dust feature that rotates with the nucleus, the center of light can shift periodically. The astrometric centroid can move around the nucleus in a repeating pattern. If observations sample rotation phase unevenly, the average centroid offset can be non-zero and can drift as the sampling changes. This can create an apparent acceleration that is actually a sampling bias. Even if the force on the nucleus is negligible, the measured positions can show a coherent pattern that looks dynamical. A strong diagnostic is to search for periodicity in the astrometric residuals that matches the photometric period. If such periodicity exists, centroid modulation is implicated. If residuals remain after correcting for such modulation, a dynamical acceleration becomes more plausible. Shape and surface roughness influence thermal recoil in complex ways. Facets at different angles heat differently. Rough surfaces can create self-shadowing and self-heating, altering the temperature distribution. Concavities can trap heat. These effects can produce a net recoil that is not aligned with simple expectations. A very irregular body can produce a recoil that includes out-of-plane components. Without a shape model, these possibilities remain broad. However, the direction of the inferred acceleration can still be compared to what is plausible given a range of spin axis orientations. If the inferred direction requires an implausible alignment, thermal recoil becomes less likely. If it can be accommodated by plausible orientations, it remains viable. Rotation also controls outgassing. A localized active area will be illuminated only during certain rotation phases. Gas production can pulse. If thermal inertia is significant, the pulse may lag behind sunlight, producing an offset in thrust direction. Over many rotations, the average thrust can be stable if the rotation is stable and the active area persists. If the active area changes, for example, by depletion or by new exposure, the average thrust can change. Therefore, an acceleration that changes gradually can be explained by evolving activity on a rotating body. An acceleration that changes abruptly could be explained by an outburst, a surface collapse, or the exposure of fresh, volatile material. Such events often produce detectable brightness changes and morphological changes, which become important correlates. An additional physical pathway arises when rotation is fast enough to stress the body. If an object spins up, centrifugal forces increase. Weakly bound aggregates can shed material. Shedding creates dust, which changes brightness and can change centroid bias. Shedding can also change the object's mass distribution and thus its rotation, creating further evolution. In extreme cases, shedding can produce fragments, and the observed light could shift between fragments, causing sudden astrometric shifts that are not dynamical acceleration of a single body. This can produce a strong illusion of unexplained motion. The test is imaging and photometry. Fragmentation often produces changes in brightness, changes in morphology, and sometimes multiple components in high-resolution images. Without such evidence, fragmentation remains speculative, but it is a known natural pathway. In a robust analysis, rotation state is constrained by assembling a light-curve dataset that spans many nights. Observations are made in consistent filters when possible to reduce color effects. The light curve is analyzed for periodicity, amplitude, and changes. If a stable period is found, it provides a foundation for modeling thermal recoil and for predicting jet modulation. If no stable period is found, the analysis accepts that rotation may be complex, and it treats non-gravitational forces as potentially time variable. This changes the modeling approach. Instead of fitting a single constant acceleration, one might fit piecewise accelerations or include stochastic terms, but such approaches require strong data to avoid overfitting. The guiding principle remains prediction. Any more complex model must improve forecasting, not just retroactively fit. Rotation constraints also guide the interpretation of the phrase, no natural cause. If the object is tumbling and faint, a simple model's failure is expected. The failure is not evidence of new physics. It is evidence that the force averaging is complex and the measurement is challenging. If the object is rotating stably and appears point-like, and yet a persistent acceleration remains that cannot be matched by outgassing radiation pressure or thermal recoil within plausible bounds, then the modeling gap becomes sharper. Even then, the likely resolution is not exotic forces, but a missing constraint on size density or activity or a subtle centroid bias that survives basic tests. By the end of this region, the role of rotation is clear. It controls the directionality and time variability of natural forces, and it controls the stability of the measured centroid in the presence of asymmetric emission. It can turn a simple physical mechanism into a complex observational signature. Therefore, a claim that there is no natural cause must be preceded by a demonstration that rotation state has been constrained, or at least that the residual pattern does not correlate with rotation or with morphology in ways that would point to centroid modulation. The next inward step returns to gravitational environment in a different sense, examining whether any overlooked gravitational interactions, fragmentation, or binary behavior could be confusing what is being measured, because these are additional natural pathways to apparent acceleration that do not require any new force model, but do require careful identification of what object is being tracked. Even after non-gravitational mechanisms and rotation-linked complexities are considered, there remains a class of natural explanations that can create the appearance of unexplained acceleration without invoking any new force on a single intact nucleus. These explanations arise from what is being tracked. Orbit determination assumes that all astrometric points refer to the same physical body, and more specifically, to its center of mass. If that assumption is violated, residual patterns can appear that are coherent and persistent, yet do not reflect a true acceleration of a single object. This region therefore examines identification-level pathways, fragmentation binarity, and subtle gravitational interactions that can alter motion in ways that seem surprising when the orbit is first interpreted. Fragmentation is a natural behavior for small bodies, especially those that experience thermal stress, outgassing pressure, or rotational stress. When a body fragments, the pieces follow similar but not identical trajectories because they separate with small relative velocities. The separation speeds can be small, but over time the pieces drift apart. If only one piece dominates brightness, at first the astrometry traces that piece. If dominance later shifts to another piece, or if the pieces overlap in the seeing disk and the combined centroid shifts, the measured positions can jump or drift. An orbit fit that assumes a single body will then show residual structure. The fit may interpret the structure as a non-gravitational acceleration because it is the simplest way to absorb systematic deviations. Yet the true situation would be multiple bodies with slightly different trajectories. Fragmentation can be subtle. It does not always produce a dramatic visual split in typical seeing. It can produce a diffuse coma with embedded condensations. It can produce a trailing dust feature. It can produce a slow change in brightness as fragments evolve. Therefore, the absence of a clearly resolved split does not rule fragmentation out. The test is to look for photometric and morphological signatures, sudden brightening or fading changes in the shape of the point spread function, persistent elongation, aligned with the motion or with the tail or inconsistent astrometry between observatories that use different aperture sizes. High-resolution imaging is particularly valuable. If multiple condensations are present, they can sometimes be detected. If not, fragmentation remains a hypothesis that must be handled carefully, but it provides a natural pathway for an apparent acceleration. Binary behavior provides a similar pathway without disruption. A binary is two bodies orbiting a common center of mass. The center of mass follows a smooth trajectory. The center of light, however, can move as the components orbit and as their brightness ratio changes with phase and rotation. If the separation is small compared to the seeing disk, the pair is unresolved. The measured centroid can shift periodically. If the sampling of the binary orbit is uneven, the centroid shifts can create an apparent drift. Over time, this can resemble a non-gravitational acceleration, especially if the orbit fit is tight and the residual pattern is coherent. The signature would be periodic residuals, or a residual pattern that correlates with photometric variations. Again, high-resolution imaging and careful light curve analysis are the tests. A binary is a natural configuration for small bodies, and unresolved binarity has been seen in various contexts. It is therefore part of the plausible explanation set. There is also the possibility that the object is not a single stable photometric entity because its coma changes. If an active object develops a jet that brightens and then fades, the brightest region of the coma can shift. The centroid can track the jet rather than the nucleus. This is not fragmentation, but it produces similar consequences in astrometry. The measured position does not correspond to a single physical point. In the orbit fit, this can masquerade as acceleration. The tests are again morphology and method dependence, but the point here is that the identity of the measured centroid can be unstable even when the nucleus is intact. Gravitational interactions can also create surprises without any new physics, but they must be treated with care because they are predictable and therefore are either included already or can be included. A close encounter with a planet can deflect a trajectory. If early orbit solutions did not capture the true path, the timing and distance of such an encounter might be misestimated. As the orbit is refined, the encounter geometry can shift and the predicted trajectory can change. This can be misread as acceleration. However, once the orbit is tight, a close encounters effect is simply part of the gravitational baseline and does not produce residuals if modeled correctly. Therefore, if residuals remain after the baseline is complete, a close encounter is unlikely to be the explanation unless the encounter involves a body not included in the model. The largest asteroids can be included as additional perturbing masses when precision demands it. Their influence is usually subtle, but in some cases it can matter. If including them changes residual structure, the acceleration claim weakens because the effect was gravitational and omitted. Yet for most observation arcs and precision levels, this influence is small compared to typical astrometric uncertainties. Still, in a disciplined analysis, sensitivity to such perturbations can be tested. If the acceleration disappears when major asteroid perturbations are included, the cause is found. If it does not, the cause lies elsewhere. A more delicate gravitational possibility is that the orbit is being fit across a boundary where different dynamical regimes produce similar sky tracks over short spans. For instance, a slightly hyperbolic and a very long period bound orbit can look similar over a limited arc. Small non-gravitational terms can also shift, which regime appears favored. In such cases, changes in classification can appear dramatic. Yet classification changes are not acceleration. They are model selection under uncertainty. Therefore, if the headline is driven by claims that the object should be unbound, but appears bound or vice versa, the proper interpretation is that the orbit remains sensitive to small forces and to measurement biases. This sensitivity is natural and common in cases near boundaries. Returning to fragmentation and binarity, these identity-level pathways are particularly relevant when a headline claims no natural cause. They demonstrate that the system being modeled may not match the model's assumptions. A single-body point mass model cannot represent a fragmenting object, an unresolved binary, or an object whose center of light is decoupled from its nucleus. The failure of the model in such cases is not a failure of physics. It is a failure of the representation. Therefore, the natural response is to test whether the object behaves like a single, stable point source. This includes deep imaging to search for multiple condensations, examining the point spread function, for elongation tracking, photometric evolution, for sudden changes, and comparing astrometry from different aperture choices. A practical diagnostic is consistency across apertures and across seeing conditions. If the inferred acceleration changes when the data set is restricted to small aperture good-seeing observations, it suggests that extended structure is influencing astrometry. If the inferred acceleration persists, it suggests either a real force or an identity-level issue that affects even the best data, such as an unresolved binary with separation below typical seeing. Another diagnostic is whether residuals show periodicity that could be tied to a binary orbit or to rotation-modulated centroid shifts. Periodicity would argue against a simple constant force and in favor of a moving center of light. By the end of this region, the set of natural explanations for apparent acceleration is broadened in a specific way. It is not broadened by adding new forces. It is broadened by questioning whether the measured point corresponds to a single stable body. Fragmentation binarity and centroid decoupling are all natural and can create coherent residual patterns that resemble acceleration. They are testable through imaging and photometry. If they are ruled out, the case for a real non-gravitational acceleration strengthens. If they are supported, then the acceleration claim is reframed. The observed astrometry reflects a changing light distribution or multiple bodies, and the appropriate model is not a simple acceleration term, but a representation that accounts for the object's physical multiplicity or evolving coma. The next inward step, therefore, becomes a careful reframing of what no natural cause would mean after all standard mechanisms and identity-level explanations are considered, and it becomes a mapping of which remaining uncertainties prevent a unique explanation. After gravity has been hardened, measurement biases have been stress-tested, and the standard non-gravitational and identity-level explanations have been laid out, the phrase "no natural cause" can finally be addressed in a disciplined way. In this region, no natural cause is treated not as an absolute statement, but as a statement about a constrained modeling space within the mechanisms tested and within the parameter bounds supported by available observations. The residual pattern remains unexplained. The key is that both parts matter: mechanisms tested and parameter bounds. Without parameter bounds, almost any mechanism can be stretched to fit by assuming extreme size, extreme density, extreme activity, or extreme structure. Without mechanism testing, any residual can be called anomalous prematurely. Therefore, this region makes explicit how a claim could be sharpened into a precise, honest statement, and why the sharper statement is usually far less dramatic than the headline. The first requirement for such a statement is that the residual pattern is robust. It must persist across independent observatories, and reductions survive removal of suspect data and remain significant under realistic uncertainty models. It must not be explainable as a catalog regime, change, refraction bias, timing bias, trailing bias, blending, or aperture-dependent centroid shift. It must not collapse when analysis is restricted to the best data. It must improve forward prediction when modeled as an additional acceleration or as a more complex time-variable term. If these requirements are not met, the phrase "no natural cause" is simply not supported because the effect may not be a property of the object. The second requirement is that the physical constraints are strong enough to limit the plausible parameter space. If radiation pressure is a candidate, size and mass must be bounded. If outgassing is a candidate, gas production must be constrained by spectroscopy or by deep imaging limits on activity. If thermal recoil is a candidate, spin state, and thermal inertia must be at least loosely constrained by photometry and thermal observations. If fragmentation or binarity is a candidate, high-resolution imaging must provide limits. Without these bounds, the argument cannot reach the stage where natural mechanisms are excluded. It can only reach the stage where natural mechanisms are untested or unconstrained. The third requirement is that the inferred acceleration has a direction and scaling that are inconsistent with the standard mechanisms under those bounds. For example, if the inferred acceleration is strongly radial and follows an inverse square dependence with solar distance radiation pressure or a dust-driven centroid bias would be natural fits, and outgassing could also fit depending on geometry. If the inferred acceleration is a long track and correlates with rotation period, thermal recoil becomes plausible. If the acceleration changes abruptly with a coincident photometric outburst, outgassing outbursts or fragmentation become plausible. Therefore, to claim no natural cause, the inferred acceleration must fail these pattern matches in a robust way. It must not align with the sun direction when radiation pressure is plausible. It must not align with activity indicators when outgassing is plausible. It must not align with rotation-linked expectations when thermal recoil is plausible. This is a high bar, and in practice rarely met because residual patterns are often consistent with one or more mechanisms within broad uncertainties. Even when the bar is met, the correct language remains about what is excluded, not about what is asserted. A careful statement might be that given the object's estimated size range and density range, the inferred acceleration would require an area-to-mass ratio that appears implausible for a natural body of that brightness and given spectral upper limits. Outgassing at the required rate is inconsistent with observations, and given photometry, thermal recoil at the required magnitude would require a thermal inertia and spin state outside plausible bounds, and imaging shows no extended structure that could explain centroid bias. Such a statement would still avoid declaring the acceleration has no natural cause in an absolute sense. It would declare that under the current evidence, the acceleration is not easily explained by the tested mechanisms. That is a very different claim from physics cannot explain it. This region also emphasizes that a mismatch between a model and data can arise from the model being too simple, not from nature being exotic. Non-gravitational forces can be time variable and orientation dependent. A simple constant acceleration term may be inadequate even when the underlying mechanisms are ordinary. For example, a rotating jet can produce thrust that varies with phase. A tumbling body can produce a changing thermal recoil direction. A dust coma can evolve changing centroid bias. If the analysis tests only constant or smoothly distance-dependent terms, it may find no satisfactory natural cause, but the true cause could be a more complex combination of ordinary effects. Therefore, the honest statement must include model completeness as well as mechanism completeness. If the model family is too narrow, the failure is not evidence of no natural cause. The phrase "right now" also becomes more precise here. If the acceleration is inferred over a limited time interval, the constraints must match that interval. For example, gas production limits from a particular night may not apply to a later interval if activity changes. Imaging limits may depend on seeing and depth and may miss faint coma. Photometry may miss tumbling if cadence is insufficient. Therefore, the statement must respect the time alignment between the inferred acceleration and the supporting constraints. If the acceleration is claimed to be current, the constraints must be current as well. Otherwise, the inference is mismatched. At this stage, the inward move is to map what remains uncertain. If size is still uncertain by a large factor, radiation pressure remains uncertain. If the nucleus is still not isolated from coma, centroid bias remains uncertain. If the spin state is not measured, thermal recoil remains uncertain. If spectroscopy is sparse, outgassing remains uncertain. Therefore, the likely reason a headline can claim no natural cause is that the public-facing interpretation ignores these uncertainties, while the technical situation remains one of incomplete constraints. The correct scientific posture is to treat the anomaly as provisional and to prioritize those constraints that most directly reduce degeneracy. By the end of this region, no natural cause has been translated into its only defensible form. The data currently show a robust residual drift that is not removed by known systematics and is not matched by the simplest parameterizations of standard mechanisms within the parameter, bounds currently supported by observations. Even that statement remains an interim description, not a final conclusion. The next and final inward step is to describe exactly which decisive observations and prediction tests would most efficiently convert that interim description into either a standard explanation or a revised understanding of the object's physical properties. That final step returns to the practical foundation of all such cases, forecasting and cross-validated measurement, because an effect that cannot be predicted reliably is rarely a trustworthy indicator of a new phenomenon, while an effect that can be predicted becomes a stable target for physical interpretation and constraint. The final inward step turns the remaining ambiguity into a short list of decisive tests that would either dissolve the claim of no natural cause or confine it to a narrow, well-specified residual that genuinely resists ordinary explanation under strong constraints. These tests are not abstract. They are concrete measurements and prediction checks that tighten the object's physical and dynamical description so that the residual pattern can no longer hide inside uncertainty. In practice, the path to clarity is always the same. Improve the astrometry so it traces the nucleus as directly as possible. Extend the arc so that small accelerations cannot be confused with early uncertainty, and obtain independent physical constraints that bound the parameters that control the natural mechanisms. The first test is nucleus-centered astrometry with controlled methodology. That means deep imaging with sufficient signal-to-noise that the object is detected well above background, and with an analysis that explicitly checks aperture dependence. Positions are measured with multiple apertures and multiple centroiding methods. If the measured positions shift with aperture, then extended emission is influencing the result, and any inferred acceleration is at least partly a centroid bias. If the positions are stable across apertures and methods, then the measurement is more likely tracing the nucleus. High-resolution imaging, when possible, strengthens this test by revealing whether any coma or tail exists, and by allowing a direct assessment of asymmetry. If the object is extended, then morphology must be modeled alongside dynamics rather than treated as a complication after the fact. The second test is multi-filter astrometry and photometry to probe chromatic effects and to constrain dust versus nucleus dominance. Differential chromatic refraction can be diagnosed by comparing positions in different filters at similar air mass. Dust-dominated light can have different colors than stellar reference frames, and gas emission can contaminate specific bands. Color information also helps interpret brightness changes. If brightness changes correlate with phase angle and filter in ways consistent with scattering, they may not reflect changes in activity. If brightness changes correlate with the onset of residual drift, they may indicate a physical transition, such as an outburst or mass shedding. These correlations are a powerful way to connect or decouple the dynamical signal from the object's optical behavior. The third test is spectroscopy, or narrowband observations, to constrain gas production. If outgassing is a candidate cause of acceleration, it should either be detected or constrained. Even non-detections are valuable if they provide strong upper limits. Those limits can be compared to the thrust required by the inferred acceleration given plausible mass ranges. If required production rates exceed limits, outgassing becomes less plausible as the dominant cause. If they are compatible, outgassing remains viable. The key is to align the spectroscopy timing with the interval over which acceleration is inferred, because activity can change. The fourth test is thermal infrared observation, to constrain size and albedo, which in turn constrains mass. This test is decisive for radiation pressure and thermal recoil. If size is constrained, the area-to-mass ratio can be bounded within plausible density ranges, and the maximum radiation pressure acceleration can be estimated. Similarly, thermal emission patterns and temperature behavior can constrain thermal inertia, supporting or limiting thermal recoil. Without thermal data, these mechanisms remain too flexible. With thermal data, they can be quantified. The fifth test is rotation state determination through a dedicated light curve campaign. A stable rotation period amplitude and phase behavior provide a foundation for modeling thermal recoil and for evaluating whether periodic residuals could be due to centroid modulation by rotating asymmetries. evidence of tumbling changes the expectation. It makes time-variable forces and time-variable centroid shifts more likely. If the residual pattern is stable while the object tumbles, a simple constant acceleration becomes less plausible, and measurement bias becomes more suspect. If residuals show periodicity matching rotation, centroid modulation becomes likely. Therefore, rotation data directly informs whether the acceleration is dynamical or observational. The sixth test is fragmentation and binarity diagnostics. High-resolution imaging and careful analysis of the point spread function can detect elongation or multiple condensations. Photometric behavior such as sudden brightening or fading can indicate fragmentation or mass shedding. Comparing astrometry from different apertures and from different seeing conditions can reveal unresolved multiplicity through systematic centroid shifts. If fragmentation or binarity is present, the correct model is not a single body acceleration. It is a multi-component or evolving photocenter model. Identifying this dissolves the impression of unexplained acceleration by revealing that the wrong object is being modeled. All of these tests feed into the most decisive check prediction. The object's next positions are forecast under competing models. One model is gravity only. Another includes a fitted non-gravitational acceleration term. Another may include a time-variable term motivated by rotation or by an inferred outburst. Predictions are then tested against new observations not used in the fit. The model that predicts best is the one that captures the real systematic behavior, whether that behavior is a true force or a stable observational bias. If no model predicts well, it suggests that the signal is not stable, that measurement is not tracing a stable point, or that the model family is inadequate. In that case, the phrase "no natural cause" is not justified. The correct conclusion is that the system is not yet constrained enough to support a stable inference. By the end of this step, the headline claim is reduced to its only durable form. Either the acceleration is not robust collapsing when nucleus-centered astrometry and method controls are applied, or the acceleration is robust and predictive and can be matched to one of the standard mechanisms within constrained parameters, which restores a natural cause. Or the acceleration remains robust and predictive, yet does not match standard mechanisms within the constrained parameters, which would define a genuine anomaly in the narrow scientific sense, an additional effect whose magnitude and direction are measured repeatable and inconsistent with known mechanisms under well-supported bounds. Even in that last case, the correct next move is not to claim physics cannot explain it. The correct move is to treat the anomaly as a new constraint on the object's properties or on the modeling of small body forces, because the history of such cases shows that better constraints and better models usually convert anomalies into understood phenomena. The phrase "there's no natural cause" is therefore not a conclusion that ends inquiry. It is a claim that can only be entertained after a sequence of disciplined steps, and even then it must be stated in terms of bounded models and bounded parameters. In the end, the object's behavior is either explained by gravity plus known small forces and measurement realities, or it becomes a precisely defined residual that demands more data and more careful modeling. The path to either outcome is the same slow, technical, test-driven refinement that begins with the first detection and ends with reliable prediction. The observations continue into the next nights, and the meaning of the acceleration claim changes as soon as the next data arrive. Under gravity-only prediction, the object should land within a forecast uncertainty region that is now small if the arc is long and the reductions are consistent. Under an acceleration-inclusive prediction, the object should land in a different region offset in a way that matches the inferred extra term. The difference between these predictions is not rhetorical. It is a vector on the sky, a difference in where telescopes must point and where the object should appear in the detector. When new astrometry lands, it either validates one forecast or it fails both. If it validates the acceleration-inclusive forecast repeatedly across independent sites, then a stable systematic exists. The remaining work becomes identifying whether that systematic is a force on the nucleus or a stable center of light bias. If it validates the gravity-only forecast once nucleus-centered methods are used, the acceleration claim dissolves into the recognition that earlier points were biased or underweighted. As the data deepen, physical constraints tighten. A single deep, high-resolution image can show whether the object is truly point-like or has subtle extension. If it is extended even faintly, it suggests that dust or gas is present and that astrometry must be treated as photocenter tracking unless corrected. If it is point-like and remains point-like across multiple nights and filters, the argument for a real force strengthens because one of the dominant confounders has been reduced. A light curve that repeats cleanly provides a rotation period that can be tested against any periodic structure in residuals. If residuals repeat with the same period, the measured positions are likely being modulated by rotation-linked asymmetry rather than by a steady acceleration. If residuals drift smoothly independent of rotation phase, a steady force becomes more plausible. Spectral constraints then provide the next narrowing. If gas emission is detected, outgassing becomes a natural explanation that can be quantified. If gas is not detected, but strong upper limits exist, outgassing is bounded and attention shifts to radiation pressure and thermal recoil. Thermal infrared constraints on size then either open or close those doors. If the object is larger than a certain scale radiation pressure, and thermal recoil cannot produce a large acceleration, and the remaining possibilities shift back toward subtle outgassing fragmentation-driven photocenter shifts or residual systematics. If the object is small radiation pressure and thermal recoil become more plausible, and the measured acceleration can be translated into a required area-to-mass ratio that can be checked for plausibility. In every branch, the outcome is not a declaration that physics fails. It is a refinement of what is being measured. An acceleration that is real becomes a parameter with a direction and magnitude that improves prediction, and the mechanisms that can produce it are narrowed by independent constraints. An acceleration that is apparent becomes a diagnosis of how faint structured light can bias a coordinate, and the cure becomes improved nucleus-centered reduction and morphological modeling. If the claim that there is no natural cause persists after these refinements, it does so only in a tightly bounded form, a repeatable predictive residual that remains incompatible with standard mechanisms under strong parameter bounds. Even then, it is a beginning, not an ending, because such a residual becomes a new data point for the physics of small bodies, forcing improved models of how sunlight heat, material strength, and microscale activity coupled to motion and forcing improved methods of separating photocenter from nucleus in the limiting regime of faint distant targets.